Hello, welcome back. This is Dr. Jason Harrington, and for differential equations, today we're going to talk about how to make population models. And there's actually two different types of models that we'll be using. The first one is the Malthusian model, or the exponential law, and the second one is the logistics model. All right, so first, let's go ahead and consider the population of bacteria that reproduce by simple cell division, and in our model, we assume that the growth rate is proportional to the population present. So that's the key word right there, that the growth rate is proportional to the population. We're going to be writing a derivative, because when we talk about growth rate, that's saying the derivative is going to be k times that population. So if I said dp over dt is equal to k times p, that's literally the model. Now this assumption is consistent with observation of bacterial growth, as long as you see that there are sufficient space and ample food supply for the bacteria. We can also assume that the death rate is 0. So what's happening is that in this particular model, we're just assuming that things are just growing and populating. Now, since the growth rate is proportional to the population present, this is our model. So this is our growth rate, and we're going to have K1, which is our constant of proportionality, and then we have times P. So that's what this particular statement says. And we can create a mathematical model. So this is our model, and then we have P naught is going to be our population, our initial population. Now we're going to assume that K1 is positive, so that there's going to be actual growth. If not, it would be decay, and that's perfectly okay. So if you ever read a math problem and it says that, a culture is dying, for example, all that means is that you do the same thing I'm going to do, but this can just be a negative number. So in a nutshell, if you basically just leave this just be any constant plus or minus, at the end you can see, is it increasing or decreasing? Is it growing or decaying? And that also works for things like when you have radioactive material that decays over time. This is the model that you would use, and just the K1 would be negative. Now, for human populations and really large animals, the death rate is 0 is certainly wrong, right? However, if we assume that people die of natural causes, we might expect that the death rate is also proportional, K2, to the size of the population. So now we have a new model. dp over dt is equal to some constant times p. This will be our growth. And then you have another constant times p, which gives us our death of natural causes. But check this out. You can factor out the p, and then you get a constant minus a constant, so we're just going to call that new constant k. How about that? It's the same model. Now we're going to assume again that the death of natural causes isn't going to be so much so that more people are dying than people are being born, and that's what this means. And again, it could be negative if you have a society or a culture dying off due to disease or whatnot. But in most healthy cases, you're going to assume that the k is greater than 0, so that you actually have exponential growth. All right, so now let's talk about this Malthusian or exponential law. And you'll notice this is a very popular differential equation that you probably already solved before many, many times as homework and practice. But if you let P denote the population, K is greater than 0 is the constant proportionality. Again, if the society, or maybe you're talking about radioactive decay, then the K would be negative. But if you're talking about growth and things increasing, then the K is positive. But again, the K can be positive or negative, really. And P naught is the population at T is equal to 0. So you have this little ordinary differential equation, which is nice and easy. And then you also have your initial conditions over here. P0 is equal to P naught. And a couple of observations about this model. It's an autonomous ordinary differential equation, and it's separable, right? Because what I can do is I can write dp over dt is just equal to k times p. And then I can write 1 over p dp is just equal to k dt. And that's really easy to integrate, because on the left-hand side, you get the natural log of the absolute values of p, and then on the right-hand side, you get k times t. And once you do all that, and then put your constants into place, you have this really nice, easy solution. Now for humans, this model works well to predict population for small t values. So if there's not that much death occurring, then this model actually works really nice. So for example, if I want to predict what would the population be of my city next year, or maybe within a decade, then the Malthusian or exponential law is pretty reasonable. But you don't want to use the Malthusian or exponential law for, say, a species of animals in the long run. Like you want to say, okay, what is a species going to do in 1,000 years or 100 years, right? Because what happens is that the solution curve is unbounded, which means that this thing is growing, again, exponentially. Now, something that was funny about this is that a long time ago when people were trying to make models for population of planet Earth, right, they would use this Malthusian model, and then they discovered that, I think it was something really ridiculous, like by the year 1980, the whole population of planet Earth would be, in the trillions, and there would be so many people there that people would be living on oceans and stuff like that. And that didn't happen, right, obviously. At least I hope not. I haven't left my room in a while. But the point is that people saw there was flaws in this model. So without further ado, let's go ahead and solve one. All right, so this example here, we're going to talk about how alligators have grown and shown up in places. In particular, in 1980, the population of alligators on the Kennedy Space Center grounds was estimated to be about 1,500. In 2006, the population had grown to an estimated 6,000. Using the Malthusian law, or exponential law for population growth, estimate the alligator population on the Kennedy Space Center grounds in the year 2020. Or in other words, what do you think it should be today? Okay, so in this, what I'm going to do to make my life a little bit easier is when t is equal to 0, right, that's going to correspond to 1980. That'll make the calculations a little bit easier. And I also know that in that particular year we had 1,500. Okay. And the population had grown to an estimated in 2006. So in other words, when t was equal to, now to go from 1980 to 2006, we're going to do 2006 minus 1980, which gives us 26. So when t is equal to 26, which is in the year 2006, our population was 6,000. So our p of 26 is equal to 6,000. So these are all givens. I haven't really done any equations yet or worked with it. Now the nice thing is that once you've solved this thing, basically you can just write out what it's going to be, right? We had the equation was going to be p of t is going to be equal to p naught e to the kt. So if we fill this out, we know that our p sub naught is 1,500. So p of t is just equal to 1,500 e to the kt. Now we don't know what k is, but that's what this is for. So we use this second bit of information to find k. So for this, I know that if I put p of 26 in there, I get 1,500 e to the k times 26 is equal to 6,000. All right, now I need to simply solve for k. So I have 1,500 e to the k times 26 is equal to 6,000. And remember, this is the little guy we want. That's what we want from that. So I'm going to have e to the k times 26 is equal to 6,000 divided by 1,500. And again, I can sort of slash that out and just make that 60 over 15, which works out to a really nice number 4. All right, so if I take the natural log of both sides, I have k times 26 is equal to the natural log of 4 So that means that k is equal to the natural log of 4 divided by 26. And again, you could type this part into your calculator to see what happens. So for this, I get 0.53319. So I get 53319. Now when you do these kind of calculations, the thing you want to do is sometimes just leave the natural log of 4 divided by 26 into the equation, and then just leave as much simplified form as you can so that you don't have any rounding errors at the end, because that's also a big issue some people have. So now let's go back to this. So now we have P of t is equal to P naught e to the kt, and we know everything now. We know P naught, that was given to us initially, and we know what k is from our second part. So we have P of t is equal to, let's see, we're going to have 1,500 e to the 0.53319 t. Now that's not the question. The question says we want to estimate what happens after the alligator population in the year 2020. So in the year 2020, so now we're going to have t is equal to 2020, but we have to subtract off 1980, our base year, right? And that's going to give us 40. So really what this whole question is asking us to do now is ask us, what is P of 40? So that's going to be about 1,500 e to the 0.53319 times 40, and we see that we have an estimate which is roughly about, so P of 40 is roughly about 12,700. Make sure I read that right. And that's how many are estimated. Now what's cool is that they haven't collected the data yet for the Kennedy Center. So I'm kind of curious to see how close this is, right? I may have used, 20 years may be pushing it for the Malthus model, but it'd be interesting to see how close it is. Now the Malthusian model has a couple of flaws to it. For example, it grows exponentially, right? And typically humans haven't overpopulated the Earth to the point where we're living in the oceans and living on Mars and such already. So the question is, what actually went wrong? Well, the Malthusian model really only considered natural death, but it didn't consider any like premature deaths due to malnutrition, inadequate medical supplies, communal diseases, violent crimes, etc. There's all kinds of different things that were not even considered. So here's what I have. I'm going to let A and B be constants, and I'm going to talk a little bit about where all this comes from. And P naught is the initial population at t is equal to 0, just like before. But now we're going to have P times A minus B P. And I'll talk a little bit about why that is. So here's just the quick concept for that. So notice that with the exponential law, we have dp over dt is going to be equal to some constant times p of t. Now the next question is, well, what happens if this is a function? Say, what happens if this is not constant? So consider this to be a function of p. What happens then? And again, you can change it to figure out what this would look like. Now what I'm going to do is I'm going to consider the new case. I'm going to consider dp over dt is just equal to a function of p times p. And the question is, what would make a really good function there? And here's what happens. If I have a graph, now I want to be able to graph f of p, but notice that if I were to solve for f of p, this is what I would get. I would get 1 over p times dp over dt is equal to f of p. So that's kind of an unusual function. Now here's how this works. So I'm going to have p here, so I input p, and then I output, say, 1 over p dp over dt here. And what happens is, let's suppose I have a model that's just linear and that's decreasing. And let's see if that would make sense. So for here I would have some initial rate of change, 1 over p dp dt. So I'd have 0 comma r. And then the population is going to have a maximum. So that's when the population is going to be 0. So I'm going to call that a carrying capacity. So that's just going to be k comma 0. And this is a line. That's linear. Now, what this says is that k is the carrying capacity, which we'll talk about a little bit more. But the carrying capacity just really indicates what a civilization could handle, or what a society could handle if there was no more growths of buildings, for example. So I used to make a model of Gainesville, and I would say, okay, what happens if there's no more housing, no more new houses ever built, and Gainesville stayed exactly the same it is today? How many people could it hold in, say, 1,000 years or something? Which is interesting, because then that can tell you, sort of what the barriers are. So K is the carrying capacity, and in other words, I just want to say that a population can have no more than K people, or K resources, however you want to put that. And of course I made it linear. And some of you may say, well, why didn't I just, make a different curve? Like maybe it comes down here, or maybe it's over there. And the answer is, well, yeah, you can do that, but it's just harder to solve. And also note that f of k is equal to 0. But if you ever have any spare time and you say, okay, I want to change this model, you certainly can, and as long as you have reasons for doing so. But I'm going to assume, for simplicity, that f is a line, and it passes through the points k comma 0 and 0 comma r. So then I have f of p that's just going to be, just using the slope-intercept form, you get r over k times p plus r. So if you put this back into dp over dt, then that means I'm going to have dp over dt. And again, I'm just going to substitute this back into the equation that I have way up here. You can remember that, way back up here. So plug that back in there, and I'm going to have negative r over k times p plus r times p, which I can just rewrite this as p times, put the p in front, and just make this 2r minus r over k times p. And then I'm just going to relabel these. I'm just going to say, let's just call this little guy A, and let's just call this little guy B. Then after relabeling, we have dp over dt is equal to p a minus b times p. And that's what you end up with. And again, you may say, well, why does this model work? We assumed linearity for several reasons, and you can Google all these things. But really the idea is that if it was linear, it would be a little bit easier to solve. If you try to make it too complicated, the ODEs become very dangerously convoluted very quickly. Now here's a couple things to notice before we move on. This model is also an autonomous ODE. The solution curve will not tend to infinity like the Malthusian model. The limit of this curve is called a carrying capacity. I mentioned it before, and I'll do some examples. It is useful for determining the largest population a non-growing city can hold. And I mean non-growing in the sense of the city itself. Like if the buildings were fixed, if all the resources were completely fixed at a certain rate inside that city, then this is the maximum capacity it could have. You could solve this by separation. Now I got to be careful here because it's not as trivial as the previous one. All right, so now let's buckle in on our seatbelts and hold on tight. There's just a lot of little algebra things that's with exponentials and such. But now let's go ahead and try to solve this thing. So, like I said before, this is separable. So I get 1 over p times a minus b times p dp equals to dt. All right, so now I got to do some partial fraction decomposition here. So I have 1 over a divided by p plus b over a divided by a minus b of p. And this whole thing is times dp. And then that's equal to dt. Now we can integrate both sides, and once we do, so let's just go ahead and integrate. Then what we have is 1 over a, natural log of the absolute value of p, plus b over a, don't forget the negative 1 over b, natural log of the absolute value of a minus bp is equal to t plus c. Okay, now you'll notice that each one of these little guys has a 1 over a in it, so I can go ahead and factor that out. And then the b's cancel, which is really nice. So then I have 1 over a times the natural log of the absolute value of p minus the natural log of the absolute value of a minus b times p is equal to t plus c. So then I can combine these two natural logs and bring the a to the other side. So now I'm going to have the natural log of the absolute value of p divided by a minus bp is equal to at plus ac. Okay, now I'm going to raise both sides to the power of e, so I get p divided by a minus bp, which is equal to e to the at times e to the ac. And again, this part here, this is just a constant. It's just a constant, which I will call C1. And again, it can be plus or minus because of the absolute values that we have in front. So then I have BP divided by A minus BP is equal to C1 E to the AT. All right. Now, let me write off where we left off last time. A divided by A minus BP, it's a tongue twister, E to the AT. Not really, I'm just bad at that. Now, next thing I'm going to do is I'm going to take the denominator and bring it to the other side and multiply it out. So then I'll have P is equal to A C1 E to the AT minus B P C1 E to the AT. Now remember, the goal of this is to solve for P. So I'm looking for this particular P here. So I'm going to bring this little guy back to the other side. So that's going to turn into P plus B P C1 E to the AT is going to be equal to A C1 E to the AT. Now I can factor out a P. So I have P times 1 plus B C1 E to the AT is equal to AC1 e to the AT, and then I can divide everything through. So now I'll have P of t is just equal to AC1 e to the AT divided by 1 plus b times C1 e to the AT. Now note, we said our initial conditions was P naught. So if I put P naught into there, just really quickly, P naught, that's just going to turn into AC1 divided by 1 plus BC1 equal to P naught. And what I can do is sort of solve, I can solve for C1 and plug that back in there. So that tells me that, and again, I want to solve for C1. I told you to hold on. Got to buckle up here. This, I'm going to now take this expression and multiply that out. So I get AC1 is equal to, and when I bring this to the other side, I'm going to go ahead and distribute it out. I'm going to have P naught plus P naught BC1. Now I bring this to the other side and factor it out. So now I have C1 times A minus B times P naught is equal to P naught. So that means that C1 is equal to P naught divided by A minus B P naught. Okay. Now what does that say? So I'm going to plug this, just remember what I'm doing here. I'm going to plug this, everything's in terms of A, B, P, and naught. And I'm going to put it back into that. So now I have P of t is equal to A P naught A minus B P naught e to the AT divided by 1 plus B times P naught divided by A minus B P naught e to the AT. All right, now here's what I'm going to do next. I'm going to now multiply this by e to the negative AT on both the top and the bottom. So now I only have one exponential functions to multiply, and I'm also going to multiply by A minus B P naught, A minus B P naught, to get rid of those fractions. I mean, honestly, I hate fractions within fractions. Nothing annoys me more. Right? There's a fine line between a numerator and a denominator. So once I do this, and I distribute this out, it cleans up quite nicely. So now I'm going to be left with P of t, now the top, right, is only going to be left with A P naught. That's the only thing that was left over, the denominator, which becomes B P naught plus A minus B P naught e to the negative AT. Okay, whew. Now, just like last time, once we derive this big mamma jamma, we can just use it. All right, now let's go on to the next slide here. Oh wow, I did it right. I mean, yes, of course I derived that correctly. But if you want to find the solution to this logistics equation of this form, then that becomes a nice little equation. And you can just use this equation, by the way. You don't have to rederive all that stuff every single time. You can just simply write this equation out and just use it as is. Now note that the limit as t goes to infinity of P of t, that's just going to be A P naught, because this term here, this goes to 0. And the bottom becomes B P naught. So the P naughts cancel, just leaving you with A over B, which is our carrying capacity. So that's going to be what's called our carrying capacity. And then we also have that the limit as t goes to negative infinity, of course, is going to be 0. So if you go back in time, then it goes to 0. And also note the limit as t goes to negative infinity for p sub t, that's going to be equal to 0. Now, just to give you an idea for how this thing actually looks, here's a specific one that I just made up. It doesn't really go with any species or population growth, but you kind of see the idea of what's happening. So here's my logistics model, and I made a slope field diagram, and you can see that if I put in 0, I get 1 for the red, and if I put in 0 for the blue, I get 3. And you can see what happens. So given the resources of a city or a country or any region really, if you have more people than can support it, then the population will then decrease to the carrying capacity. If you're under that, so if your place where you live has lots of resources and lots of places people can live, but they're not utilizing that, and you have a lot more growth than people, then your society can grow, but it will meet the carrying capacity for that. And what else is really cool is that because of this example that I made, you'll notice that A is just equal to 2, and then of course my B is just equal to 1, so that's basically just 1 times P. And you see that the carrying capacity is in fact K, which I'll call K, A over B, which is 2. And so you can see that on this line where 2 is, you have this carrying capacity. Now, just like any model that you have, you'll also note that the solution P of t is just 2, just a constant function. Not only satisfies it, but you can also see that it is a solution. So 0, which is down here, and 2 is a solution. So if your population is already at the carrying capacity, then it will neither grow nor decay. It just is constant. If your population is at 0, well, there's no growth or decay. It's just 0. So anytime you're off of that a little bit, so for example, if I'm just off of it a little bit, then you'll see that the curve will grow. Otherwise, it's not. So here's an example. You have biologists stocked a lake with 800 fish and estimated the carrying capacity to be 79,000. The number of fish grew to 1,070 in the first year. How long will it take for the population to increase to 3,950? Okay, so here's what you do. We know that we're going to have this model that we have dp over dt is equal to p times a minus b times p. And we're actually given, certain things are just given to us right off the bat. Like in this case, it's interesting that they gave us the carrying capacity, which is 7,900. So we know that we're going to have a over b, and we have a divided by b is just equal to 79,000. So let's see if we can use this information. Now again, you don't have to solve the ODE like you did before or anything. You can just use the equation. So here we're going to have a times p naught divided by b times p naught plus a minus b p naught e to the negative a t. All right. Now, to make the substitutions, what I'll do is just easily solve for a. So a is just equal to 79,000 times b. And up here, we're given that we were stocked with 800 fish, assuming that there were no other fish of that type in the lake, we also know that P naught is equal to 800. So now let's make this the substitution. Now this again is more algebra than calculus. You probably won't. We're not even taking a derivative. We're not even integrating. We're literally just using algebra. So I substitute everything back in. I'm going to replace, and this is, don't forget to note, this and this turns into 79,000 times B, and everywhere I see a P naught, that turns into 800. So we have a lot of little substitutions to do first before I even get started with anything. So we have x of t is going to be equal to 7,900 times b times 800. So I made those substitutions. The b below is going to be equal to b, which we don't know what that is yet, but we do know it's times 800, plus the next one we're going to have 7,900 b, because I changed the a to that term, minus b times 800 e to the negative at. Now I'm going to leave this as a, because believe me, there's a lot going on here. I just don't want to mess that up. So if I multiply all this stuff out nicely, in the first case, what I'm going to do is just multiply this out. So if I multiply that out, I'm going to get 6,320,000. 2, 3. I'll put little commas in here so it's easier to see. Divide it by, and I can factor out a b. So each little term here, that has a b, this has a b, so I can factor this b out of that, and then I can factor b out of the whole denominator. So let's do that. B. Oh, and in the numerator, I got too excited about the b's. And the denominator has a b and the numerator has a b. So don't forget this little guy up here. I like b's, they're kind of cute. Times 800 plus 7,100 e to the negative at. Alright, so now my b's cancel, and I'm left with 6,320,000. 6,020,000 divided by 800 plus 7,100 e to the negative at. Now I can factor 100 out of the bottom and just get rid of those zeros, so I can just simply write this as, let's see, as that. So now I have x of t is going to be equal to, that's going to turn into 63,200, still not great, but better than what we had before, 8 plus 71 e to the negative at. Now let's keep going. So I have x of t is equal to 63200, so I have 63,200, divided by 8 plus 71 e to the negative at. All right, now we were given that in 1 year there was 1,070 fishes. So we were given that when t is equal to 1 year later, that's 1 year later, we have p of 1 is equal to 1,070. Okay, so let's make that substitution in there and see what happens. So if I put that in there, I get x of 1 is equal to 63,200 divided by 8 plus 71 e to the negative a, which is equal to just 1,070. Okay, so now if I divide everything through, I will have 1 divided by 8 plus 71e to the negative a is going to be equal to 1070 divided by 63,200. And again, I can cross out a 1, just making that 107. And then I'm going to just divide that by 6,320. Okay, now if I take the reciprocal of both sides, then I'm going to have 8 plus 71e to the negative a is going to be equal to 6,320 over 107. So then that's going to leave me with 71e to the negative a is just going to be equal to 5,464 divided by 107. And then I'm going to take that number and divide by 71. So I should get e to the negative a is equal to 5,464 divided by 7,597. You take the natural log of both sides, and you get the natural log of this big thing, 5464 divided by 7,597, which is going to be equal to, let's see, that's going to be equal to negative 0.32957231. And that just means that A is equal to 0.32957231. Oh my goodness. Sometimes I don't like application problems because in real life, numbers are horrible, horrible things. Okay, now, remember that now that we have A, we also have B. Remember, because B was just equal to A times that carrying capacity, which was initially back at 7,900. So remember, this was our little carrying capacity. Okay, so just please bear with me for a second. We now have a formula for all this jazz. We have A times P naught divided by B P naught plus A minus B P naught e to the negative a t. Okay, and we make all of our substitutions back in there. So A, and I'm just going to rewrite all this down, and this is what we should get. A of t is equal to this big equation here, 263.65784 ... The bottom is going to be 2603.62125. And I'm trying to keep all the digits in the calculator when I just make my substitutions. Minus 20896.67 ... But I'll just leave it at that. E to the negative 0.329523 t. Oh my goodness. Wow. That's pretty cool. Now the next question says, we didn't actually solve it. So the question was when will it reach half capacity? So remember, capacity was, so the question was, when will we reach half capacity? And that can be done with just saying, when is this just equal to half capacity? So it's 7,900 divided by 2, which is equal to 3,950. So let's go ahead and solve that. All right. Now, again, I'm just going to start with this just like I did before. For me, it's easier to write down variables than it is to write down a whole bunch of numbers. Some of you are actually the opposite. You like to write down a whole bunch of numbers. I'm not like that. There are like 3 types of mathematicians, you know, those that can count and those that can't. So here's what we have. I'm going to set this equal to half. And you can simply write this in as, you know, you can write it in as A over B, half of the carrying capacity, or you can just simply write in the number 3,950. It doesn't quite matter. Now, just to make sure that all the numbers work out, let's just go ahead and I'll just keep the number here. And just like before, you're going to do the same sort of tricks, same sort of algebra tricks. So you have A P naught divided by B P naught plus A minus B P naught. The best thing to do is just to store all these variables in your calculator, or write them down up the side and then at the end plug them all in. 3,950. So the first thing I'm going to do is just I'm going to put this on the other side. So I have 1 over B P naught plus A minus B P naught e to the negative AT. That whole thing is just going to be equal to 3,950 divided by A P naught. And again, what else you can do is just rewrite this. Remember, you always have this relationship. I might as well just use it instead of having to write the 3,950. So this should just turn into A divided by 2B, or naught, times A P naught, like peanut, I guess. And the A's cancel, and that's a little bit easier to write instead of having to write 3,950. And again, you can be as clever as you want. So now I'm going to take the reciprocal of both sides. So I have B P naught plus A minus B P naught e to the negative AT is just going to be equal to 2B P naught. Then I'm going to subtract off B P naught from both sides. Hey, that's kind of cute. You get A minus B P naught e to the negative AT. That's just going to be B P naught. Wow, I really like it when things like that happen. Okay, so now divide both sides. So I have e to the negative AT is going to be equal to B P naught divided by A minus B P naught. And now I'm going to take the natural log of both sides. So now I have negative AT is equal to the natural log of B P naught divided by A minus B P naught. And then just multiply everything by negative A. So I have T is equal to negative 1 over A times the natural log of the absolute value of B P naught divided by A minus B P naught. Now, I'll let you leave all the calculations at home because, well, really that's the hard part. Now, let me show you something sneaky that I did in all this, other than all the algebra stuff. Notice now I have found the time for when it reaches the half of the capacity. And I did it in general. I didn't do it for that specific particular problem because, remember, this equation up here that I have, A over 2B, is actually the general equation for half of the capacity. So now every time you see a question that asks you when is the time for the half capacity, for example, it's always going to be this equation. which is kind of neat. That's another reason why I like to solve things in general, because once you do this and you have an equation, you can use it for all the other problems that ever ask you that, which is kind of neat. All right, well, that concludes this lecture. And remember, please, it's all really algebra.